All right, welcome back to Introduction to Computer Networks. And this is Polly streaming live from NTU again. Yes, hi. Hi, Ali, Yuan Hao, and Noe. And you know what? Let's do what we usually do, go through the announcements. So the first 2 points are trivial now, right? The links to the video session here and the link to the Google Meet session. Bullet 3, the point 3 is always about the assignments due this week. Now you probably notice. So what are they? PA2, quiz 5, 6, and 7 will be due this Saturday. And what's new and special this week is this. There's a Google spreadsheet generated. If you click into this link below here, you should see this document. So look at the block on the upper right of your screen. So it's a Google spreadsheet. There are 3 tables. First table is called PA. Second table is called quiz. Third table is called participation. And I guess you figured out what they are, don't you? So first table, PA, records your progress of your PA assignments. Okay, so at the top, you see the PA numbers, and on the left, you see the team numbers. Okay, so you can see that the TA is very efficient, finished grading PA 1 already. And by the way, Team 3, if you are here, could you contact the TA as soon as you can? So this table, straightforward. Sometimes when you receive the PA grades, and it's somehow deducted some points, there will be comments from the TA behind. So if you scroll to the right, you will see comments for your PA3, comments for your PA4. Okay, so from here you can tell why you get deducted a certain fraction of the points. Now, quiz table. It's also straightforward, right? At the top you see the quiz number. On the left you see the team number. And to understand the table, for example, this block, if you receive a 1, that means Team 4 have completed quiz 2. Okay, and so these 1s will add up, and the completion rate will count towards 25% of the quiz grade. And in case you see a highlight in your block, that means these highlighted blocks will add up and count towards the extra effort part of the quiz grade. That's 5%. And last table is the participation. So from this table, you see that, it's listed weekly. So we have the week 1 and week 2 of the participation grades ready. And you see that each week you earned participation points in 5 categories. So this is participation, how active you are on the YouTube chat. So for example, you guys are very active, right? Sally, Yu Jie, Cheng En, Yu Ji, Ting Xuan, Yu Ting, and LA representation. So, hey, these counts are what you guys are doing here on the YouTube chat. Okay. And the second category is participation on the score server. Third category is if you call in during the office hour. And this is email exchange with Polly. And this last column is to account your interaction with the TA. Okay, good. Now some of you might see that, hey, what a coincidence. We have a lot of 5 here. Okay, it's not exactly that they all participated 5 times. It's more that we cap the participation, each category, each week up to 5. So this is so that we pace you and you will continue to participate throughout the semester. All right, good. So that explains the Google spreadsheet, and for some of you this might be very important so you can track your progress. All right, so with that said, we move on with the lectures. Today we also have 3 groups of topics. First is very fast, just to wrap up circuit switching. We've already introduced circuit switching, and it's quite straightforward. We just have a tiny little bit to talk about today. Second is to introduce this new principle called packet switching. It's quite opposite of circuit switching, but it's very important because this is the principle used when the internet is designed. And the internet is the network we'll be talking about the whole semester. Okay, so we'll be spending quite a bit of time there talking about packet switching. And the last one is also going to be short. It's to introduce the structure of the internet. And you will see how the internet evolves from the older times to the modern times. Great. And let's start with the circuit switching, the first thing we'll talk about. So let's recall circuit switching a little bit. Okay. What it does is this. Before a user can send data, we need to reserve resources and set up a circuit. Then the data can be transmitted. Okay, so you see that to set up the circuit, it will take time. And that time is called the call setup time. That is also saying if someone has data to send, from that point on, until the time the packet or the data is received at the receiving end, it will be what? The call setup time plus the time to push all the bits through the circuit, isn't it? Yeah. That's the total time to get a data or a file transferred. And that is something that we want to talk about using a numerical example to illustrate how you calculate the transfer time in a circuit switch network. So, how long does it take to send a file this big from a sender to a receiver over a circuit switch network? And the assumptions are these. All links running the same bandwidth, and each link use TDM to divide the resource into pieces, and we divide the resource into what? 24 pieces. So between A and B, the effective bandwidth is what? 1.536 megabits per second divided by 24. Okay, and how much is this? Guys, if you have a calculator at hand, could you help me out here? Okay. Let me know what the value is on the chat, okay? So now we have the effective bandwidth. Hey, we want to transfer this file. And this is 640 kbits divided by A, right? So this will be the total time to push all the bits through the circuit. So let's make it B. And you know what? Hey, the total time to pass the data, okay, from the data being generated is what? The call setup time, and that's half a second. So B plus half a second. Now, C here is the total time it takes to send this file from A to B. Okay? Let's see. Oh, thank you guys. Yeah. And Nico is the first. 64. 0.064. Yeah, I guess it's 0.064 megabits per second. So this is, then it's probably 64 kilobits per second, right? And if this is 64 kilobits per second, B equals 10. And therefore, C equals what? 10.5 seconds. There we go. And now you can understand, last week, Polly said that, hey, to me, circuit switching is simple. It's simple in a way that it's simple to derive what the performance is going to be. And it's easy to anticipate how the data will travel the network. All right? So that's all about circuit switching. Let's move on to the next topic, packet switching. Thank you. Thank you, guys. And you know what? Packet switching, it's very important. Okay, so this video introduces packet switching. You want to pay attention. Make sure that you capture the strengths of packet switching and the weaknesses of packet switching. And by the way, Polly tries to speed up these videos a little bit because depending on how challenging how complicated the content is. Okay, and in fact, in this next video, the strengths and the weaknesses are quite obvious. So you can see that probably tune up the video speed a little bit. Okay, that's because that chances low that you miss the strengths and the weaknesses. Now let's discuss more about packet switching. The mechanism is very simple, right? We simply cut the data into small packets, and as the link is available, pass it out. So each of these small packets will go on the link in full bandwidth. So if you consider L being the size of the packet length, and R being the link bandwidth or the link rate, the delay, this being small, this being large, to send a packet very small. This is one advantage. And then think about this: if you get two users, A and B, both are generating data and both are sending these packets out. If A is idle, not sending, and B comes up with data, B can send out, no problem, and in full link bandwidth. Similarly, if B is idle and A has data, no problem sending out. So there's no such a situation in circuit switching where B allocates all the resource, gets all the resource, and A having data to send, but A didn't get any resource as a result. B sitting idle, occupying all the resource, and yet A having lots of data wanting to send, not getting anything. Okay, so there's no idle waste there. Last is maybe a little bit less obvious. You see, bandwidth is used as full, so there's no need of dividing the link bandwidth into pieces. So the mechanism is also simple. Okay, being simple, there's no idle waste, and there's no call setup, resource reservation process required. Okay, packet switching can potentially be very efficient, especially for short data streams. Think about the resource reservation delay, the call setup time. It can be pretty long, and if you have very short data stream, then hey, the overhead relative to the entire need of sending data is high. So you can probably imagine now, data network, internet. At the beginning, we were just sending really short emails. It doesn't make a whole lot of sense just to send an email and you go all the way to set up a circuit. So another advantage of using packet switching is also because of the user demand. Now let's look at what's wrong with packet switching. First of all, we will have resource contention because there's no reservation mechanism. What if A and B, they all have a lot of data to send, so the resource demand is beyond the available resource. So we call that situation network congestion. In that particular situation, packets will have to queue up at these routers and wait for link queues. So you see here, wait, the keyword. Delay here to transmit a packet is short, but there could potentially be wait that is a little bit uncertainly long. Okay. And hey, packets will get queued. What if there's not enough space in the queue? Packets also get dropped. So in packet switch network, we do have substantial delay. We could have substantial packet losses. One big disadvantage. Another disadvantage is here. This one is a little bit subtle. In packet switching network, there's no circuit being established. The way we send packet is that you forward it out on the link. The next router will need to pick up everything. So you need to wait until the entire packet is received. The next router will need to receive the complete packet before the router can further forward the packet. So this is called store and forward. So the router action there passing packets is store the packet first and then forward the packet next. So this mechanism here is determining how packets are moved, okay, one hop at a time. Meaning you have one of these L divided by R every hop, every router. All right. Do you like packet switching? You see that the keyword in circuit switching is reservation, and the resource is exclusively allocated to a particular user. But in packet switching is what? It's sharing, right? The opposite of reservation, sharing. What's nice is that you use the full bandwidth to transmit data all the time. But the downside is, yeah, if are so inclusive, okay, of all the data to be sent, then when the resource is not enough, then you have this thing called congestion, or sometimes called contention. And so you could have long wait, you could have packet drops. The performance of a packet switch network is less deterministic. It's much harder to calculate, unlike the example we just saw. And there's also something called store and forward that adds delay. Every hop, every router the packet needs to travel through. Okay, so good, sharing, high utilization, bad, congestion, and undeterministic performance. Okay, hard to predict, hard to anticipate. Now, next video is to explain more, because we just introduced this property, store and forward, in packet switch network. Next video is to give you an example to illustrate what store and forward is, and how when the number of routers the packet need to travel gets more, then the delay gets longer. In circuit switch network, hey, over a circuit, you just calculate by dividing the data size to the bandwidth once. But in packet switch network, for every hop, you need to add amount of delay doing that calculation. You will see in this video. Okay. So here let me illustrate the store and forward effect to the end-to-end delay. So consider this scenario. The source is over here. Okay, user typing up things and generating these small packets, 1, 2, 3. One router here in the middle and receiver on the other side. And each packet here the user is generating is L bits long, and the link bandwidth is R bps. So you see, to send this big packet over the link at this speed, this is the amount of time that's required. And on a packet switch network, we need to store the packet entirely before forwarding. So entire packet needs to arrive at the router before it can be transmitted further. The end-to-end delay will be what? 1L divided by R for this hopping, because this guy, to send it out, it requires L divided by R. This router here receiving it waits until all is received, and then what? Send it out again. That's another L divided by R. So if L is 7.5 megabits per second, R is 1.5. You see, each hop, 5 seconds. 2 hops, in this case, how long? 10 seconds. 3 hops, the longer, the more hops you have, the delay of sending the packets longer. This is different from circuit switch network. Bits can be streamlined. Okay, there's no need to store a bunch of bits first before forwarding it. Okay, that is saying that each bit arriving here gets out quickly, so there's no hopping. It's just the propagation delay and the transmission delay, L divided by R, from the first hop. This slide is to illustrate congestion. The scenario is A and B, 2 users generating packets, A generating A generating green packets, and B here generating blue packets. And you see these packets are generated as user A and user B are typing things up spontaneously. So green and blue, they will kind of bunch up or multiplex in a random order. Okay. Unlike in TDM, time division multiplexing, everything goes rotating, rhythmic. And this, okay, having some sort of spontaneous behavior in it is statistical multiplexing. Okay, so on packet switch network or on the data network internet, yeah, packet kind of, multiplex to each other randomly, spontaneously, depending on how they are generated. Now let me draw your attention here, the router. You see packets in case the outgoing link bandwidth small. And incoming link here, this is 100 megabits per second Ethernet. This is only 1.5 going out. Chances very high, A and B, if both of them actively generating lots of packets, yeah, the packets will have to wait here in the queue. before they get the link queues. And if there's not enough space here for the queue, the next one, the green one coming here, will need to be dropped. But there's no memory space to hold. And those packets waiting in the queue, yeah, it depends on how long the queue is as they comes in to the router. The queuing delay can vary. It can be a little uncertain. But transmission delay, the time it takes to go on this link is always the packet size divided by what? 1.5 megabits per second. And we use the full link bandwidth. So transmission delay here is very easy to get. All right, so that was packet switching, store and forward, and how chaotic things can be. Okay, these packets meeting each other, waiting in the queue, and potentially get dropped. Now, next is I'm going to show you an example, again, numerically, to contrast CS and PS in its performance. And this example, guys, sorry, it's a little bit more biased towards PS because the scenario is a little bit closer to what engineers thought of designing the internet. So internet was designed originally to send just short messages, such as emails. Okay, so you can see the scenario is a little bit more like that. Here, let me use an example to illustrate. Packet switching actually outperforms circuit switching when there are more users, and each of these users are not exactly very active, sending short messages only each time. All right, so scenario is very simple. Okay, we do have a network of end users, and they're behind this router. Going out of the router is a very low bandwidth link, 1 megabits per second. And each of the users is behaving this way. When they're active, they do need a lot of bandwidth, 100 kilobits per second. But they're only 10% of the time active. In a circuit switch network, in order to satisfy these 10 users, and each at maximum requires 100 kilobits per second, so we reserve 100 kilobits per second to each of the users. And how many users we are allowed to reserve bandwidth? This is 1,000 kilobits, so we can only allow 10 users, okay? 10 circuits. But in packet switching, you see, the users are only active at 10% of the time. Consider this scenario. If we have 35 users, right, the only situation that these 35 users will have trouble sending data out is when there's at least 10 users being active at the same time. So what is the probability of these 35 users and more than 10 of them being active at the same time? If you do the calculation, you'll see that it's very low. So 99.9996% of the time, in packet switch network, 35 users will do well. No trouble. So if you do have a lot more users and each of the users needs just a small portion of time to send data, which one would you pick? Circuit switching or packet switching? It's quite obvious, isn't it? And oh, by the way, anyone here knows how to derive this value? The probability of 10 of the users being active at the same time, given the active rate is 10%. All right, so if you know how to calculate that 0.0004, okay, for 35 users being, for more than 10 users out of the 35 being active at the same time, post it on Discord, post it on random, okay, extra credit for that. All right, and it's time to go on to the quiz today. Okay, this is quiz 5. So we've heard about circuit switching. Yeah, the keyword is reservation. We've heard about packet switching. We heard that the packets will be mixed-maxed and a little bit chaotically moving around the network. Okay, so let's use an analogy. How about using water transfer network as an analogy? So building pipelines to transfer water will be what? The circuit switching way. But put the waters into smaller buckets and pass them around, that will be the packet switching way. Okay, so quiz 5 asks you this. Q1, consider the car network. This is the network that we are familiar with. Okay. Do you think car network is operated based on the circuit switching principle or packet switching? What's more important is whatever you say it is, argue for why. Justify your choice. Similarly, for the train network. Q3, I'm asking you, between circuit switching and packet switching, which one do you like better? So this is very subjective, of course. Okay, think it through, pick one, and tell us why. Guys, and this is one of those open-ended quizzes, so you'll be given a sufficient amount of time to gather your teammates and discuss. So let's move to the score first. August. Okay, hey, August. Hey, you were not patient and wait until the end of describing the quiz. Hey, you need to tell also why. Hey, so hey, bad demonstration. So you guys will be given time. So gather your teammates. You have 7 minutes to discuss and 1 minute to type your solution up. And it's okay to have split decision. Okay, so that's start counting time. Okay, 7 minutes plus 1. All right, so let's check out what you guys said. So it's very interesting. Every semester, the preferences, the majority of the preferences are a little bit different. Okay, so this year I see that packet switching seems to be preferred more. But you guys also have different opinions about whether the car network or train networks are circuit switched or packet switched. But I see the majority seems to be saying that the car network is packet switched. So cars get, if you are in a car network, chances very high that you are congested, right? So you consider the car itself is the packet that you're sending. I agree. And for the train network, more are saying, just like Team 1 here, circuit switched. Because a train would ride on the track and the path is fixed, okay? And it's predetermined. Even the time the train will leave and the time they're supposed to arrive. Okay, so it definitely explaining the car network and train network this way. Think of car and train network this way. They are indeed car network more packet switching, train network more circuit switching. And the reason that Team 1 prefers PS is because the telephone network that is running on the CS, the circuit switching principle, is dead. Okay, hey, it's almost dead. Okay. And by the way, Team 1 has also split opinion. So Ryan here chipped in. I disagree on number 3. Yeah, because CS is preferred because CS, when the utilization of the trains is high, it is cheaper, right? It's what the most of the mass metropolitan systems are hoping for. Okay, but if the utilization is low, right? Tricky, isn't it, Ryan? Team 9. Team 2 also has a disagreement. Now, okay, it's okay. Okay to be yourself, guys. Okay, and Team 9, Jun Huan, I think. Sorry, in case I pronounced the names wrong. Packet switching for the car, circuit switching for the train. And this is very detailed explanation. Thank you. Okay, Team 9. And you guys like packet switching more? Yeah, it is more flexible, isn't it? Especially when the resources are abundant. Team 7 says car circuit switching because each car is individual and separated. Oh, interesting. I think you're thinking that the car carrying people and the data will be the people. And so people in a car is exclusive a resource, okay, to be transported. Interesting. Very different perspective. Very unique. Train. Packet switching carries collected freights. Interesting, interesting. I guess people go on and off the train, right? And so car having many, a train having carts, a collection of carts, it's almost like packets, right? A flight of packets. I see. It allows more users based on the examples that we've seen in the class. All right, so yeah, I understand. You guys are all very opinionated, which is a good thing. As you read other teams' answers, you can see also that, hey, one likes packet switching, the other likes circuit switching. So for example, Team 15 also split opinion for quiz for Q3, right? One likes PS, the other likes CS, right? You say, they say, so one prefer another, one prefer one than another. And you can argue either way. Yeah, it's okay. Please, guys, openly welcome opposite opinions, okay? Usually from speaking the opposite opinions, you guys discover what might be a better way to approach a problem. It's better to have more opinions than having no opinions. Great, guys. Hey. So due to time constraint, I would definitely go on and read all you guys' opinions. And if I see interesting one, I will definitely provide feedback. Oh, Team 2. Wow. Very long split opinion. Okay, thank you. So, yeah, so I'll come back to you guys' answer, Team 2. Let's come back to the lecture. And before we start the lecture, yeah, there are a few questions. For example, Junhuan was asking, packet size is something that we can decide. And is there like an optimum size such that the efficiency will be higher, will be the best? I'll talk about this after I introduce why packet size needs to be small. Okay, and you will also see that when packet size is too small, it might not be so good either, because each packet has a packet header that allows the router to make decisions to decide where to pass the packet on. Okay, so Junhuan will definitely come back to your question before the end of the lecture today. And Zhongwen just strict. Okay, so I guess you are part of team 2. Okay, and you don't want your voice to be unheard. I see. Okay, it's okay. Now, last video comparing circuit switching and packet switching. Now you know none of these is a slam dunk. Okay, good or bad, one way or the other. After the discussion trying to solve the quiz, what do you think? Packet switching versus circuit switching. Do you think packet switching is the slam dunk winner? Is data network internet's way always gonna win? Probably not always, isn't it? It's great for short bursty data, right? Short amount of time but sending lots of data, because it promotes maximum resource sharing and it's quite simple, no code setup either. But on the other hand, we do have congestion. Packet delay might be unexpected long, and probably worse, there could be packet losses. And so you need additional protocols, because of the way the very low level packet forwardings are designed. So we probably need extra mechanism at the higher layer to ensure data can be transferred in a reliable way if it's necessary. And what if we want to do some level of a guarantee, for example, to do video streaming? Can we achieve circuit-like behavior with packet switching philosophy at a very low level? Can we do bandwidth guarantee? Well, people have been thinking about it, and this is still a problem that's not quite yet solved. And this is covered in chapter 9, the multimedia networking chapter, later on in the textbook. And we unfortunately won't have time to cover this semester. Yeah, so that video serves as a summary comparing circuit switching and packet switching. Okay. Now, let's talk a bit more about packet switching. First is about the packet size. Why we prefer the packet size being small. It's explained in this video. The next few slides, they are still somewhat important, okay, but not strictly talking about packet switching, circuit switching, and the comparison. So these slides are to answer a couple important questions. We said that packet switching, what it does is to divide data stream into small packets. But why not large packages, right? We didn't really justify that. We kind of like that L divided by R. The time it takes to send one packet is small because this is small. And in case the link is really fast, then this is small. But if this is a little bit larger, well, not so bad either, isn't it? Well, think again. And this is the example that I try to use to set up the stage. And it's just a slightly extended version of the previous example where we have 2 hops only, just one router between the source and destination. The packet size 7.5 megabits and the link rate 1.5 megabits per second. And you see that L divided by R is 5 seconds. And because there are 3 hops, so this time store 5 seconds, 4, store 5 seconds, 4, and 5 more seconds to store. Altogether, 15 seconds to send this packet L. Now, 7.5 megabits, large, right? Sending a large package like this over this 3-hop network, 15 seconds. Let's try dividing this large message into smaller packets and see how it will work. 7.5 megabits, let's divide them into 5,000 packets. This way, each packet is only this big, 1.5K. Link rate is still what? 1.5 megabits. So to send a small packet like this, it takes only 1 millisecond. Now, look at this. This is the same network, 3 hops. Each packet is now very small. And to send one packet, the first router will take 1 millisecond to receive it and then send it out. So 1 millisecond, 2 millisecond, and only 3 milliseconds until the destination receive the first packet. And you know what? These links can work in parallel, right? Because router 1 here can be passing packet 1 while the source start passing packet 2. You are trying to do also streamlining here, except that the unit of streamlining is a small packet. You see, Why packet switching suggests small packets? Because it's trying to maintain the benefit of doing circuit switching. Unfortunately, we could not be streamlining bits, okay? But let's keep the packet small. Then we get to keep some of these nice properties in a circuit switch network. And having these links that can work independently is nice. We can pipeline or streamline the sending of the packets over the network. So each link works in parallel. And the overall delay in the end is what? 5,002 milliseconds, only 5.002 seconds. If you recall earlier, if we send 5,000 small packets altogether, 7.5 megabits, each hop 5 seconds, and 3 hops 15 seconds. How much time are we saving? Big time, isn't it? This is why in packet switching, people always talk about cutting data into small packets. Yeah, now you see, smaller packets, the better in terms of the delay to transmit the data. But hey guys, there's when you're sending a packet, it's not like every bit in the packet are all data. So there's in a packet, there's a part of it being the control messages. For example, the destination address, of this data. So only a portion of the whole packet are the data bits. So you don't want to send 1 bit data because then that control part of the packet, that's a fixed size and it's significant. So if you send just 1 bit data, the overhead, the overall good put of sending data will be really low because the overhead is high, the control part is high, the real data part is low. So Junhuan, that is why you want to send small packets, but not too small. You see? I hope that you get it. Now, in order to find the optimum data part of the packet, it really depends on the network and the size of the control part. So one can actually formulate a problem for you to compute what is the optimal packet size. So Polly might write a problem in the exam 1 so you guys can work on it. How about that? And August, I totally understand what you're saying. You know that there's a control part that is called the packet header, right? So the best utilization of the bandwidth is, of course, send as many data bits as possible, right? And then the utilization is the highest. The packet header overhead is the lowest. But totally agree with you. If such a packet is dropping the network, you need to retransmit everything again. Yeah. So obviously, you don't want the data to be. You don't want the data part to be too big. So this is again another good reason why we don't want the packets to be large. And that is to add on top of what I just said. Yes, the internet usually has 1500 byte limitation, but sometimes we have different link layer technologies these days. That 1500 bytes might get cut down to some degree as they travel through certain different links, where the links limit the packet size further. So we'll see that in, I think, chapter 4. Or chapter 3 or chapter 4. All right, so I hope that explains Junhuan's question and also echo what August is contributing. Which is, yeah, so it's a little bit lower than 1500 byte, right? And so, yeah, that's all the time we have, guys. If you have other questions, feel free to type them up on the chat or go on to the Discord and post it in Ask Us Anything. For those who don't, I say goodbye. I see you tomorrow morning. So we are not quite yet done finishing talking about packet switching. So we'll talk about store and forward a little bit more. Why it's necessary to do store and forward. Why can't we just streamline the bits? See you tomorrow morning. Bye. All right. Where's my music? There you go. Bye. See ya. Bye. Bye, Sally. I see the audience is very diverse. I know Yu Ting. Interesting. Train. Interesting. A little reservation based. Yeah, so if you consider transferring from one train to another, right? Enter or leave the road at any time. More users. All right. Good. We'll go on same route together. interesting. Okay. I think it's time to end the stream, so let's end the stream now.